In this part, I would like to discuss some practical aspects related to calibration. Therefore, we're going to start with an overview of the most important calibration experiments that I used. And these are the rotating drum experiments. You see it here. The drum is filled with the particles, and then we measure the so-called dynamic angle of repose as a function of the rotation rate here. So the angle of repose here, dynamic angle of repose, will be this angle that forms between the bed surface and a horizontal line. One can also use avalanching statistics or some shape metrics of this free interface here. This is less usual. A second very important calibration experiment is a ring shear or annular shear cell. Here we measure the yield loci of the granular material as a function of the consolidation stress. With that, also the bulk density of the material can be easily measured. Also, the flow function can be determined, but this is also less usual. The beautiful thing is that the yield locus is not a single point, but has multiple output parameters. A third important type of calibration experiments are hopper or container fill emptying experiments. Here you see on the left a cylindrical conical shaped hopper. Here we can measure the flow rate, the mass flow rate exiting the hopper, and the angle of repose. As you will see here in this experiment, we can easily determine multiple angle of repose. So whether we look at this interface here or this interface, we can define then at least two different angle of repose, that of essentially the forming heap and that of the heap that is drained. Let us close the discussion of angle of repose with an important statement. A plurality of angle of repose definitions exist, so we have to be careful whether we consider an experiment where we discharge from a cylindrical container or where we have a rotating drum or another setup. For the same material, we can measure different angle of repose, and the important thing is simply to use the same measurement from the experiment and compare it with the analogous result that is calculated with the DEM simulation. Let us now focus on the two different methods to perform the actual calibration. The first method is direct simulation. Here we choose an initial parameter set. This set can be, for example, based on prior knowledge. We then run our DEM simulator, and the result of the DEM simulation will be compared to the experiment. The critical point here is that the calibration tool will then decide on the next set of parameters. The tool will then again restart the simulator and again compare the key quantity with the experimental result. And this loop goes on and on, let's say 7, 8, 10 times, and then we should have a set of parameters. What you see here is that we can only compare it to one single key parameter. If we want to match multiple key parameters, we have to run this in series. The other method is called here the response surface-based method. Here we run first simulations for a large parameter space. For example, we pick two key influence parameters. Let it be the particle-particle and particle-wall friction coefficient. And then we construct out of this data a so-called response surface. This is also called the surrogate model. We can then easily compare this response surface with our experimental results. And out of this comparison we then gain the correct set of parameters. Let us illustrate this with a practical example. What we have here is a list of simulation runs that feature different combinations of particle-particle and particle-wall friction coefficients. You see here already the response of the DEM simulation. Let us now have a look at the result of these set of DEM simulations. What you see is that for these three simulations at the top, we have a very small angle of repose, and changing the particle-particle and particle-wall friction coefficient, we can nicely see the change in the response of the DEM simulator. We can now visualize this in such a surface plot. So here you see the particle-particle friction coefficient, and here you see the particle-wall friction coefficient. As your intuition will tell you, the higher the particle-particle and particle-wall friction coefficient, the higher will be the dynamic angle of repose. But a very critical point has to be made here again. Any value of the dynamic angle of repose, let it be for example 15, can be realized with a combination of two of these friction coefficients. So if we intersect this plane here with a horizontal plane at 15, for example, we will get a line. And this line tells us the combination of particle-particle and particle-wall friction coefficients that will give this specific angle of repose. Thus, we need as many output parameters as calibrated parameters. In short, a single angle of repose is not enough to calibrate two friction parameters, for example. This is again visualized here. So here you see the contour lines of the angle of repose, dynamic angle of repose. And for example, if we say we have an uncertainty of plus minus 0.5 degree because of our post-processing routines, for example, we'll see that in this region here, we can create this result. If the angle of repose that we are aiming for is 11, we would obtain this region, for example. So we need a second experiment in addition to this experiment number 1, and this can be, for example, the angle of repose in a different setup, for example, in a cylindrical setup. And now the magic happens. If we now combine the response surfaces from experiment 1 and from experiment 2, we can simply intersect those two regions that are quantified by this yellow and violet line and identify the region of the friction coefficients that give for both experiments the right answer. And this is what it means to do a response surface-based calibration, namely to overlay at the end those intersecting lines. So again, the confidence region here from experiment 1 and the confidence region from experiment 2 are overlaid to arrive at the overlapping region that is then the result of our calibration procedure. That is it for this part. I hope you enjoyed it. See you next time.